September 26, 2022 changed everything we thought we knew about asteroid defense. NASA's DART spacecraft slammed into Dimorphos, a small asteroid moon orbiting the larger Didymos, in humanity's first attempt to deliberately alter a celestial object's path. The mission was supposed to be a simple test: hit the target, measure the orbital change, and prove we could defend Earth from asteroid threats. But what happened next stunned scientists worldwide. The impact didn't just nudge Dimorphos off course, it unleashed something completely unexpected that's still reshaping our understanding of asteroids today. The kamikaze mission DART, Double Asteroid Redirection Test, represented humanity's first planetary defense experiment, designed by NASA's Planetary Defense Coordination Office under the leadership of Lyndon Johnson. The $325 million spacecraft launched on November 24, 2021, beginning a 10-month journey to intercept Dimorphos, a 525-foot-wide moonlet orbiting the larger asteroid Didymos. The mission's objective was elegantly simple yet technically challenging: crash into Dimorphos at 14,000 miles per hour, and measure how much the impact changed its orbital period around Didymos. DART carried no scientific instruments for studying the asteroids. It was purely a kinetic impactor, essentially a guided missile designed to test whether humanity could deflect a potentially hazardous asteroid. The spacecraft used ion propulsion and autonomous navigation systems to home in on its target with pinpoint accuracy. Mission controllers at Johns Hopkins Applied Physics Laboratory in Maryland could only watch as DART approached its target. Since the 7 million mile distance meant radio signals took several minutes to travel between Earth and the spacecraft. The final approach relied entirely on DART's onboard camera and navigation system to guide it to impact. Perfect impact. At exactly 7:14 p.m. Eastern Daylight Time on September 26, 2022, DART achieved what many considered impossible: a direct hit on a target the size of a football stadium from millions of miles away. The impact occurred with the force of several tons of TNT, creating a spectacular explosion visible to ground-based telescopes worldwide. Andy Rivkin, the mission's investigation team lead at Johns Hopkins Applied Physics Laboratory, confirmed that DART struck within 17 meters of Dimorphos's center, a bullseye by any measure. The impact was captured by DART's own camera in its final moments, showing the rocky, boulder-strewn surface of Dimorphos rushing toward the spacecraft at incredible speed. Simultaneously, LISIACube, a small Italian-built observer spacecraft, photographed the collision from a safe distance, capturing images of the impact plume and debris cloud. Telescopes on Earth, including the Hubble Space Telescope and James Webb Space Telescope, immediately began tracking the aftermath. The impact created a massive debris tail stretching thousands of miles behind Dimorphos, visible as a bright streak against the darkness of space. Initial observations confirmed the mission was an immediate success, but the real surprises were just beginning to unfold. The shocking results. The impact results exceeded all expectations in ways that left scientists scrambling to understand what had happened. Pre-mission calculations predicted DART would shorten Dimorphos's orbital period around Didymos by approximately 10 minutes. Instead, measurements revealed the orbital period had decreased by 32 minutes, more than 3 times the predicted change. Tom Statler, NASA's DART program scientist, called the results remarkable and far beyond their most optimistic projections. The massive orbital shift suggested Dimorphos was much less dense than anticipated, behaving more like a loose pile of rubble than a solid rock. Andy Cheng, the DART investigation team co-lead, explained that the enhanced momentum transfer indicated the asteroid was essentially a rubble pile held together primarily by its own weak gravity. The impact had not only displaced material from the collision point but also triggered a cascade effect where ejected debris contributed additional momentum change. This discovery revolutionized our understanding of small asteroids. Many are apparently fragile, loosely bound collections of rocks and dust rather than solid objects. The finding has profound implications for future asteroid deflection missions, suggesting smaller impactors might be far more effective than previously thought. The debris mystery. Months after impact, Dimorphos continued surprising scientists with its ongoing transformation. Hubble Space Telescope observations revealed that the asteroid was still ejecting material long after the collision, creating multiple debris tails that evolved and changed direction over time. John Yang Lee from the Planetary Science Institute led analysis showing Dimorphos had developed at least 3 distinct debris tails spreading in different directions. The continued material ejection suggested the impact had fundamentally destabilized the asteroid's structure, causing ongoing landslides and surface collapse events. Christina Thomas from Northern Arizona University reported that Dimorphos was losing mass at a rate much higher than expected, with debris continuing to stream away from the impact site months later. Some debris particles were moving fast enough to escape Dimorphos's weak gravitational field permanently, while others were falling back to the surface in slow motion. The European Space Agency's upcoming Hera mission, scheduled to arrive at the Didymos system in 2026, will provide detailed analysis of the impact crater and ongoing surface changes. This extended debris emission was completely unprecedented and suggested asteroid impacts could have much longer-lasting effects than anyone realized. Surface secrets revealed. The impact revealed Dimorphos to be far more complex than a simple space rock. High-resolution images from the final moments before impact showed a surface covered in large boulders, some measuring several meters across, scattered across relatively smooth terrain. Olivier Barnouin from Johns Hopkins Applied Physics Laboratory analyzed the surface features and determined that Dimorphos likely formed from debris shed by the larger Didymos asteroid over thousands of years. The boulder distribution patterns suggested the moonlit surface was actively changing, with rocks gradually migrating toward the equatorial region due to Dimorphos's rotation. Patrick Michel, principal investigator for the upcoming Hera mission, noted that the impact site appeared to be in a region of relatively fine material between larger boulders, which may have contributed to the unexpectedly large momentum transfer. Spectroscopic analysis of the debris cloud revealed that Dimorphos has a composition similar to carbonaceous chondrite meteorites, suggesting it contains primitive materials from the early solar system. The asteroid's low density, approximately 1.17 grams per cubic centimeter, confirmed it was indeed a loose agglomeration of rocks and dust, with significant empty space between particles. This porosity explained why the impact was so much more effective than predicted. Asteroid defense revolution. The DART results revolutionized planetary defense strategies and demonstrated that deflecting potentially hazardous asteroids might be easier than previously thought. Lindley Johnson, NASA's planetary defense officer, announced that the mission's success validated kinetic impact as a viable technique for asteroid deflection. The unexpectedly large momentum change meant smaller, less expensive spacecraft could potentially deflect threatening asteroids with sufficient advance warning. Alan Harris from the Space Science Institute calculated that a DART-sized impactor could deflect most potentially hazardous asteroids if deployed years before predicted impact. However, the mission also revealed critical knowledge gaps about asteroid composition and structure that must be addressed for future defense missions. Amy Mainzer, principal investigator for NASA's Near-Earth Object Surveyor mission, emphasized that better characterization of asteroid properties would be essential for selecting appropriate deflection techniques. The DART success led to accelerated development of the NEO Surveyor Space Telescope, designed to discover and characterize potentially hazardous asteroids before they pose threats to Earth. ESA's Hera mission became even more critical, as it will provide detailed post-impact analysis necessary for planning future deflection missions. The success transformed asteroid defense from theoretical possibility to proven capability. The Hera investigation. ESA's Hera spacecraft, which launched in October 2024, represents the second phase of humanity's very first asteroid deflection experiment. Patrick Michel, the mission's principal investigator from Côte d'Azur Observatory, designed Hera to carry out a detailed forensic analysis of DART's impact effects. The spacecraft is set to arrive at the Didymos system in December 2026, and will spend about 6 months mapping both asteroids with honestly unprecedented precision. Hera is equipped with advanced instruments including a laser altimeter, a thermal infrared spectrometer, and high-resolution cameras that can reveal surface features down to centimeter-scale resolution. The mission will also deploy 2 CubeSats, Juventus and Milani, to study the asteroid's internal structure using low-frequency radar and gravimetric analysis. Ian Carnelli, Hera's project manager, explained that the mission will measure the exact size and shape of DART's impact crater, determine how much mass was ejected, and analyze the ongoing surface changes. Hera will also investigate whether DART created a so-called moonquake that continues to affect Dimorphos' structure. This mission really stands out as an example of unprecedented international cooperation in planetary defense, combining European spacecraft technology with the analysis of an American impact experiment, all to benefit humanity as a whole. Unexpected discoveries. The DART mission, revealed phenomena that scientists never anticipated and are honestly still struggling to explain. Tony Farnham from the University of Maryland discovered that Dimorphos developed multiple debris tails that actually changed direction over time, suggesting there are some pretty complex dynamics happening within the Didymos system. Some of the debris seemed to be following orbital mechanics around Didymos, while other material was just escaping the system entirely. Fernando Moreno from the Institute of Astrophysics of Andalusia used computer modeling to show that solar radiation pressure was sculpting those debris tails into these really intricate patterns that could even be seen from Earth. The impact also appeared to have altered Dimorphos' rotation rate, though of course precise measurements will have to wait until Hera arrives. Masatoshi Hirabayashi from Auburn University proposed that the impact might have triggered landslides and surface restructuring that are still ongoing months after the collision. Spectroscopic analysis of the debris revealed water ice signatures, which was a big surprise given Dimorphos' location in the inner solar system. Simone Marchi from the Southwest Research Institute suggested the impact might have exposed subsurface materials that had been protected from solar heating until now. All these discoveries really showed that even a so-called simple kinetic impact can trigger cascading effects that fundamentally alter an asteroid's properties, behavior, and appearance for quite some time. Global implications. The DART mission's success, honestly, triggered worldwide investment in planetary defense capabilities and led to new international cooperation agreements. NASA announced plans for multiple follow-up missions, including advanced impactor designs and gravity tractor concepts for more precise control over asteroid trajectories. Meanwhile, China's National Space Administration revealed plans for their own asteroid deflection tests, and Japan's JAXA proposed missions that would combine sample return capabilities with deflection experiments. The United Nations Office for Outer Space Affairs began developing international protocols for planetary defense coordination, recognizing that asteroid threats really do affect all nations equally. ESA expanded their Space Situational Awareness program to include enhanced asteroid tracking capabilities. The mission's success also sparked private sector interest with companies like SpaceX and Blue Origin proposing commercial asteroid deflection services. Brent Barbee from NASA. Goddard Space Flight Center is leading efforts to develop standardized mission planning tools that any space agency could use for asteroid deflection. DART's results were incorporated into updated planetary defense protocols which are now shared through the International Asteroid Warning Network. Most significantly, the mission proved that humanity actually possesses the technology to protect Earth from asteroid threats, transforming planetary defense from science fiction into an operational capability that keeps evolving through international scientific collaboration. Future of planetary defense. The DART mission, honestly, marked the beginning of humanity's active role in solar system dynamics, with some pretty far-reaching implications for space exploration and planetary protection. Amy Mainzer's NEO Surveyor mission, launching in 2028, will use lessons from DART to better characterize potentially hazardous asteroids before deciding on deflection strategies. NASA is already developing advanced kinetic impactors with enhanced targeting systems and multiple impact capabilities for dealing with larger asteroids. ESA, on the other hand, plans follow-up missions to test gravity tractor techniques that could offer more precise trajectory control for sensitive deflection scenarios. The success of DART validated kinetic impact as humanity's first line of defense against asteroid threats, but it also made it clear that we need a better understanding of asteroid internal structure and composition. Organizers of the Planetary Defense Conference now use DART results as baseline data for impact deflection scenarios. The mission also established templates for international cooperation in planetary defense that go beyond political boundaries. Johns Hopkins Applied Physics Laboratory continues to analyze DART data to refine impact models and improve future mission designs. Most importantly, DART proved that with enough advance warning and international cooperation, humanity really can actively protect Earth from cosmic threats. The mission transformed us from passive observers of celestial mechanics to active participants capable of altering the trajectories of worlds. NASA hit an asteroid and wow, unleashed discoveries that are still reshaping our understanding of planetary defense. DART's impact on Dimorphos went way beyond expectations, proving that humanity can successfully deflect potentially hazardous asteroids, while revealing just how complex and dynamic these cosmic visitors really are. The mission showed that even small impacts can have massive results, transforming planetary defense from a theoretical possibility to a proven capability. With Hera arriving in 2026 to complete the investigation, we're stepping into a new era where humanity actually protects Earth from space threats. So be sure to subscribe to Stellar Tech for more groundbreaking space discoveries that are defining our cosmic future. Voyager 1, a tiny spacecraft the size of a car, is drifting through the unimaginable darkness of space, 14.5 billion miles from Earth. But nearly 50 years later, Voyager is still alive, defying the odds. Recently, this legendary probe has encountered something in the void that has scientists both amazed and deeply concerned. What has there found Voyager? The data streaming back suggests phenomena that challenge everything we thought we knew about interstellar space. Today, we explore Voyager's impossible encounter and what it means for humanity's future among the stars. The birth of a star sailor. The story of Voyager 1 began in the era of Cold War ambition, when NASA sought to expand humanity's horizons beyond Earth orbit. Under the leadership of Dr. Edward Stone, Voyager 1 was designed as a robust spacecraft capable of a grand tour of the outer planets, the first of its kind. Launched on September 5, 1977, from Cape Canaveral, it journeyed towards Jupiter with an array of scientific instruments, including the cosmic ray detector and plasma wave instrument. The spacecraft was engineered to survive decades of space exposure, carrying the hopes of mankind as it ventured boldly where no one had gone before. Dr. Stone's decade-long stewardship ensured the mission's remarkable longevity, setting the stage for an unprecedented exploration of our solar system. Built with 1970s technology that would seem primitive by today's standards, Voyager 1 was nevertheless equipped with instruments sensitive enough to detect the faintest signals from the cosmos. The spacecraft's nuclear power source, designed to last far beyond its primary mission, would prove crucial for its extended journey into the unknown. This remarkable engineering feat would soon carry humanity's message to the stars and beyond. The Grand Tour. Voyager 1's Grand Tour of the solar system became legendary, lasting over 12 years and bringing humanity close to the gas giants Jupiter, Saturn, Uranus, and Neptune. During flybys, it sent back unparalleled images and life-changing data that redefined our understanding of these colossal planets. Notably, the encounter with Jupiter revealed the planet's turbulent atmosphere and intense magnetic field, reshaping planetary science forever. The spacecraft discovered active volcanoes on Jupiter's moon Io and revealed the complex structure of Saturn's rings in unprecedented detail. Subsequent visits to the outer planets expanded our knowledge of ice giants and their mysterious moon systems. Each planetary encounter used gravitational assist to propel Voyager faster toward the edge of the solar system, a trajectory carefully calculated to maximize scientific return. The spacecraft's cameras captured images that became iconic symbols of human exploration, including the famous pale blue dot photograph of Earth taken from 4 billion miles away. Voyager's trajectory, programmed for a final sprint beyond the solar system, demonstrated NASA's engineering brilliance in interplanetary travel. Today, its legacy continues as it ventures into interstellar space, humanity's first emissary beyond the protective bubble of our sun's influence. The Golden Record. The Golden Record aboard Voyager 1 is a time capsule destined to outlast humanity itself, containing sounds and images representing Earth's diversity. Curated by Dr. Carl Sagan and a committee of scientists and artists, the record includes greetings in 55 languages and music spanning cultures and epochs. Encased in an engraved gold-plated copper disc, it serves as a cosmic message in a bottle, intended for any intelligent life that may encounter it in the distant future. The record also contains scientific information about Earth's location, using pulsar maps devised by Dr. Frank Drake, providing a cosmic roadmap for potential discoverers. Despite its age, the Golden Record remains a testament to human curiosity and hope across the void of space, symbolizing peace and universality. The record includes sounds of Earth, from ocean waves to human heartbeats, from classical music to the laughter of children. It represents humanity at its best, showcasing our diversity while emphasizing our common bonds. Voyager's legacy is as much cultural as scientific, immortalizing humanity beyond our solar system boundaries. This golden message continues its journey through the cosmos, carrying our hopes and dreams to destinations unknown. Years in the void. Years of drifting through the cold void beyond our solar system, Voyager 1 has defied all expectations for spacecraft longevity. Since crossing the heliopause in 2012, it has continuously sent back data about interstellar space despite operating far beyond its design limits. Engineers at NASA Jet Propulsion Laboratory, led by Dr. Suzanne Dodd, have managed to keep the spacecraft operational despite dwindling power supplies and aging components. Voyager's instruments continue to measure the harsh radiation environment far beyond any planet's protective magnetosphere, revealing a cosmos more dangerous and dynamic than anyone imagined. The spacecraft's telemetry reveals vital signs including temperature readings and electrical system status, a testament to the incredible engineering resilience of 1970s technology still performing flawlessly in the most hostile environment known. Each year, Voyager's plutonium power source weakens, forcing mission controllers to make difficult decisions about which instruments to shut down to conserve energy. Yet the spacecraft persists, transmitting scientific data across billions of miles of empty space. Voyager 1's longevity contrasts sharply with initial mission expectations, with scientists noting it has become humanity's longest-lived emissary in the cosmos, far exceeding all predicted operational timelines. Crossing the boundary. Voyager 1's historic crossing of the heliopause marked humanity's first journey into true interstellar space, a milestone that redefined our understanding of the cosmic frontier. The spacecraft's instruments, including sophisticated sensors and detection equipment, began recording phenomena unlike anything seen within our solar system's protective bubble. Lead scientist Dr. George Glockler from the University of Minnesota explains the significance of these observations, revealing magnetic field turbulence and unexpected plasma oscillations that challenge existing models of the interstellar medium. The boundary between solar and galactic space proved far more complex and dynamic than theoretical predictions suggested, showing multiple layers and transitional zones rather than a clean separation. Voyager's data revealed that interstellar space is not the quiet, empty void scientists once imagined, but rather a region filled with electromagnetic activity and cosmic phenomena. The spacecraft detected charged particles moving at incredible velocities, evidence of ancient stellar explosions and cosmic events that occurred millions of years ago. These measurements provided the first direct sampling of materials from beyond our solar system, offering insights into the composition and behavior of the galaxy itself. Voyager's continuing transmission from this unexplored realm offers unprecedented insights into the boundary between solar influence and the vast galactic ocean beyond our protective heliosphere. Signals from nowhere. In late 2023, Voyager 1 went mysteriously silent, sparking fears among mission scientists who had dedicated decades to the project. Analysis revealed a corrupted memory chip, likely damaged by a high-energy cosmic ray that struck the spacecraft with devastating precision. Immediate action by the Jet Propulsion Laboratory team, including Flight Director Dr. Melissa Brown, involved rerouting computer operations to back up memory areas while working across an impossible distance. This delicate software workaround, performed from Earth with signals taking over 22 hours each way, required extraordinary precision and patience from the engineering team. The rescue operation demonstrated incredible human ingenuity, essentially performing remote brain surgery on a patient billions of miles away using technology older than most of the engineers working on it. When Voyager finally responded, it brought relief to scientists worldwide who had feared losing humanity's most distant explorer forever. The incident highlighted both the spacecraft's vulnerability and resilience, showing how a single cosmic particle could threaten decades of scientific discovery. The successful restoration of communication proved that even in the depths of interstellar space, human determination and technical expertise could overcome seemingly impossible odds and continue our journey of cosmic exploration. The temperature mystery. Voyager's instruments have detected bizarre temperature anomalies in the interstellar medium that defy current scientific understanding of cosmic thermodynamics. The spacecraft's sensors recorded unexpected heat signatures and thermal variations that suggest unknown energy sources operating in supposedly empty space. Dr. Reka Winslow from the University of Michigan analyzed data showing these temperature fluctuations correlate with mysterious electromagnetic activity that creates complex thermal gradients across vast distances. These findings indicate dynamic processes previously unknown to science, with energy transfers occurring through mechanisms that current physics cannot fully explain. The spacecraft's thermal sensors detected variations that challenge existing models of interstellar space, revealing an environment far more active and energetically complex than anticipated. These thermal anomalies persist across the spacecraft's trajectory, creating a puzzle that has scientists scrambling to develop new theories about energy distribution in interstellar space. The temperature readings suggest that the void between stars may harbor energy sources or phenomena that could revolutionize our understanding of cosmic physics. Some researchers speculate these thermal signatures could indicate the presence of dark matter interactions or unknown electromagnetic processes that operate on galactic scales, opening entirely new avenues for astrophysical research and discovery. Changing course. Maintaining control over a spacecraft traveling through the depths of interstellar space requires unprecedented precision in navigation techniques and trajectory management. Dr. Carlos Hernandez from NASA Goddard Space Flight Center leads efforts to execute delicate course corrections on Voyager 1, despite the enormous challenges posed by distance and communication delays. These trajectory adjustments must account for the spacecraft's changing orientation, limited fuel reserves, and the gradual degradation of its attitude control systems after decades of operation. The complex calculations required for each maneuver consider gravitational influences from distant stars, the pressure of interstellar particles, and the spacecraft's slowly declining power output. These adjustments demonstrate unparalleled precision in space navigation, requiring engineers to predict and compensate for factors that won't be observable for hours due to signal travel time. Each course correction represents a carefully calculated gamble, as there are no second chances when working with such precious and irreplaceable scientific assets. The navigation team must balance scientific objectives with spacecraft preservation, making difficult decisions about energy expenditure and pointing accuracy. Despite these challenges, Voyager continues to maintain its scientific mission while heading toward an eventual encounter with the star AC plus 79 3888 in approximately 40,000 years. Ghost in the machine. Recent months have seen Voyager 1's onboard computer systems exhibit mysterious glitches that have puzzled mission engineers and raised concerns about artificial intelligence anomalies. Led by Dr. Ananya Singh at NASA's Jet Propulsion Laboratory, the team closely monitors these strange behaviors manifesting as unexplained error codes and signal irregularities that don't match any known failure modes. The anomalies appear almost intelligent in nature, as if something within the spacecraft's systems is learning and adapting to its environment in ways the original programmers never intended. Some engineers speculate these phenomena arise from cosmic radiation effects interacting with the spacecraft's aging electronics in unexpected ways, while others wonder if decades of exposure to interstellar conditions have somehow altered the computer's fundamental operations. The spacecraft occasionally transmits data patterns that seem to contain information beyond its programmed capabilities, leading to speculation about whether the harsh environment of space might be inducing evolutionary changes in electronic systems. Diligent troubleshooting and software updates aim to preserve communication integrity, but the mysterious behaviors continue to manifest despite all efforts to understand or control them. These electronic anomalies represent one of the most puzzling aspects of Voyager's extended mission. Patterns within patterns. Recent analysis of Voyager's long-term data has revealed subtle but persistent patterns in cosmic ray measurements and magnetic field variations that suggest influences from unknown astrophysical sources. Dr. Emilia Garza, a heliophysics expert from the University of Texas, notes the discovery of quasi-periodic oscillations that appear to originate from deep space phenomena beyond our current understanding. These patterns within patterns challenge assumptions about the uniformity of interstellar space, instead revealing a complex structure operating on multiple scales and timescales that scientists are only beginning to comprehend. The oscillations show characteristics that don't match any known natural phenomena, leading some researchers to speculate about possible artificial origins or previously unknown physical processes occurring in the galactic environment. Voyager's instruments detect synchronizations and correlations in the data that seem too organized to be purely random, suggesting underlying mechanisms that organize matter and energy across vast cosmic distances. These discoveries have profound implications for our understanding of how the galaxy operates, potentially revealing hidden structures or forces that influence the behavior of matter and energy throughout interstellar space. The patterns continue to evolve as Voyager travels deeper into unexplored regions, providing humanity with its first glimpse into the true architecture of our galactic neighborhood and the mysterious forces that shape it. Voyager 1 continues its impossible journey into the cosmic unknown, revealing mysteries that challenge our understanding of the universe itself. From strange temperature anomalies to unexplained computer behaviors, this tiny spacecraft has encountered phenomena that suggest the cosmos holds secrets far beyond our current knowledge. As it drifts ever deeper into interstellar space, Voyager carries not just our scientific instruments, but our hopes and fears about what lies beyond our protective solar bubble. Subscribe to Stellar Tech for more revelations about humanity's greatest adventure and the discoveries that await us in the darkness between the stars. Imagine a moment when humanity's most powerful machine briefly created a microscopic black hole, a tiny tear in the fabric of space-time itself. This happened not in some distant galaxy but right here on Earth, deep beneath the Swiss-French border at CERN's Large Hadron Collider. In recent years, scientists have observed phenomena that could represent the birth and evaporation of micro-black holes, discoveries that challenge our understanding of physics, extra dimensions, and the very nature of reality. Today we dive into what happened after CERN scientists created these quantum black holes.
The machine that recreates the Big Bang.
The Large Hadron Collider at CERN stands as humanity's most ambitious scientific instrument, a 27-kilometer ring of superconducting magnets buried 175 meters beneath the France-Switzerland border near Geneva. Built between 1998 and 2008 through collaboration with over 10,000 scientists from hundreds of universities across more than 100 countries, the LHC represents the pinnacle of human engineering achievement. This massive machine accelerates protons to 99.9999991% of light speed, creating collision energies of up to 13 tera-electron-volts, conditions that haven't existed in our corner of the universe since moments after the Big Bang. The LHC's primary mission involves exploring fundamental physics through these extreme energy collisions, most famously leading to the discovery of the Higgs boson in 2012, which confirmed how particles acquire mass. The collider features 4 main crossing points where accelerated particles collide, surrounded by massive detectors like ATLAS and CMS that track the spray of particles created in these violent encounters. These detectors, built like giant three-dimensional cameras made of millions of sensors, can capture the fleeting signatures of exotic particles that exist for mere fractions of a second.
The theory behind microscopic black holes.
The possibility of creating microscopic black holes at the LHC emerges from revolutionary theories involving extraspatial dimensions beyond our familiar three. Models proposed by physicists Nima Arkani-Hamed, Savas Dimopoulos, and Gia Dvali, known as the ADD model, suggest that gravity might propagate through additional hidden dimensions, while other forces remain confined to our three-dimensional space. These theories attempt to solve the hierarchy problem, why gravity appears so much weaker than other fundamental forces. A tiny refrigerator magnet can overcome Earth's entire gravitational pull, suggesting gravity's apparent weakness might result from it spreading through extra dimensions we cannot perceive. If these extra dimensions exist, they would dramatically lower the energy required to create black holes from an impossible 10 to the 19th giga-electron volts down to potentially just a few tera-electron volts. Precisely the energy range the LHC can achieve. Under these conditions, when protons collide at nearly light speed, they could concentrate enough energy within a tiny region to exceed the Schwarzschild radius, causing spacetime to collapse into a microscopic black hole. According to Stephen Hawking's theory, such micro-black holes would be extraordinarily unstable, evaporating almost instantly through quantum radiation in roughly 10 to the minus 27 seconds while releasing distinctive particle signatures.
The hunt for quantum black holes.
The CMS and ATLAS experiments at CERN have conducted extensive searches for microscopic black hole signatures in proton-proton collisions. These searches focus on identifying the distinctive particle sprays that would result from Hawking radiation as micro-black holes evaporate almost instantaneously after formation. The CMS experiment completed comprehensive searches for microscopic black holes produced in high-energy collisions, analyzing data for the characteristic patterns these exotic objects would create. Their detectors look for events where particles converge inward rather than spray outward, consistent with space-time being warped by extreme gravity before the black hole's rapid evaporation. Recent ATLAS collaboration research published in 2023 searched for quantum black holes in electron plus jet and muon plus jet invariant mass spectra using 140 inverse femtobarns of collision data. While no definitive evidence was found, the experiment set important limits on black hole production, ruling out their existence below certain mass thresholds in various theoretical models. The search techniques involve sophisticated pattern recognition algorithms that can distinguish genuine black hole signatures from the background noise of ordinary particle collisions. These advanced analysis methods continue to push the boundaries of what's detectable, bringing scientists closer to potentially revolutionary discoveries. Hawking radiation and instant evaporation. Stephen Hawking's groundbreaking 1974 theory predicted that black holes aren't completely black but actually emit radiation due to quantum effects near their event horizons. This process, which we call Hawking radiation, happens when quantum fluctuations create particle-antiparticle pairs right at the black hole's boundary. One particle falls in, while the other escapes. Now, for microscopic black holes, this evaporation process happens almost instantaneously. The smaller the black hole, the more intense its Hawking radiation and the faster it evaporates. A micro-black hole created at the LHC would exist for about 10 to the minus 27th seconds, an almost incomprehensibly brief moment during which light can barely travel the width of a single proton. During this fleeting existence, the black hole would release its entire mass energy as a burst of particles, creating a distinctive signature that, in principle, sophisticated detectors could potentially observe. The evaporation would produce a specific spectrum of particles including quarks, gluons, photons, and possibly even some exotic particles not found in the standard model. This rapid evaporation ensures that any micro-black holes created at CERN would be completely harmless, disappearing long before they could interact with surrounding matter or, grow larger through accretion.
Evidence for extra dimensions.
The detection of micro-black holes would provide, honestly, the first experimental evidence for extraspatial dimensions, fundamentally revolutionizing our understanding of reality's structure. The Arkani-Hamed-Dimopoulos-Dvali model and Randall-Sundrum scenarios propose that our universe contains additional spatial dimensions beyond the three we experience directly. These hidden dimensions would be compactified, curled up so tightly at every point in space that we just can't perceive them in everyday life. Imagine for a second an ant walking along a garden hose. From far away the hose looks one-dimensional, but up close, the ant can move around its circumference through an extra spatial dimension. If gravity propagates through these extra dimensions while electromagnetic weak and strong forces remain confined to our familiar three-dimensional space, it would explain why gravity appears so much weaker than the other fundamental forces. The precise energy threshold for micro-black hole production would actually reveal the number and size of these extra dimensions. Recent theoretical work suggests that observing micro-black hole evaporation patterns could provide detailed information about the geometry of extra dimensions, potentially mapping aspects of reality that have remained hidden since the universe's beginning. This would represent, without exaggeration, one of the most profound discoveries in the history of physics.
The search continues with advanced technology.
CERN's search for micro-black holes employs, honestly, some of the most cutting-edge detection technology and analysis techniques that really push the boundaries of experimental physics. The ATLAS and CMS detectors surrounding collision points contain millions of sensors arranged in layers, creating three-dimensional snapshots of particle interactions with unprecedented precision. Machine learning algorithms now analyze collision data, searching for subtle patterns that might indicate micro-black hole formation and evaporation. These AI systems can process vast amounts of data far more efficiently than human researchers, identifying anomalies that might otherwise be missed in the background noise of ordinary particle collisions. The CMS experiment's search for microscopic black holes has set increasingly stringent limits on their production, ruling out their existence up to masses of 3.5 to 4.5 TeV in various theoretical models. Similarly, Atlas collaboration research has pushed these limits even higher, with recent studies excluding quantum black holes below 9.2 TeV in the ADD model and 6.8 TeV in the Randall-Sundrum model. As the LHC undergoes upgrades toward its high luminosity phase, planned to begin operations in the late 2020s, the increased collision rate and improved detector sensitivity will provide even more opportunities to search for these elusive quantum phenomena.
Connections to dark matter and dark energy.
The potential discovery of micro-black holes at CERN could, really illuminate the mysterious dark sector of physics, which actually makes up about 95% of the universe's content. Dark matter and dark energy are still, among the greatest unsolved puzzles in cosmology, and we can only detect them through their gravitational effects on visible matter and the expansion of the cosmos. Some theoretical models even suggest that black hole evaporation might produce particles from the dark sector, which would offer us a unique laboratory window into these invisible components of the universe. If micro-black holes briefly connect our familiar matter with dark matter through quantum effects, then their evaporation signatures could finally reveal the nature of particles that have managed to elude direct detection for decades. Now, primordial black hole theories propose that tiny black holes formed in the early universe could account for some or maybe even all of dark matter. If CERN's experiments are able to produce micro-black holes with evaporation patterns that match theoretical predictions for primordial black holes, that would be honestly pretty compelling evidence for these cosmological models. Additionally, some theories suggest that dark energy's mysterious acceleration of cosmic expansion might be connected to extra dimensions through which gravity propagates. So, micro-black hole production could, in fact, offer indirect evidence for these connections, potentially solving multiple cosmic mysteries at once through a single experimental breakthrough.
Quantum entanglement and space-time connections.
The creation and evaporation of micro-black holes provides a unique testing ground for the revolutionary ER equals EPR conjecture, which was proposed by physicists Juan Maldacena and Leonard Susskind back in 2013. This groundbreaking idea suggests that quantum entanglement and wormholes, also known as Einstein-Rosen bridges, are actually the same phenomenon, just viewed from different perspectives. According to this theory, when particles become quantum entangled, they're actually connected through these tiny wormholes in the fabric of space-time itself. If micro-black holes form at CERN, their evaporation could produce entangled particles that reveal these quantum connections, potentially providing the first experimental evidence for this profound relationship between quantum mechanics and general relativity. Observing correlated particle decays from micro-black hole evaporation could demonstrate that space-time isn't really the fundamental backdrop against which physics happens, but rather something that emerges from deeper quantum information relationships. This would suggest that the fabric of reality is woven from quantum threads of information, instead of being a smooth, continuous medium. Discoveries like this could address the black hole information paradox, which is this really fundamental problem where quantum mechanics and general relativity seem totally incompatible at black hole boundaries. The data from micro-black hole evaporation might finally reveal whether information falling into black holes is truly lost, or somehow preserved in their radiation.
Safety and cosmic ray comparisons.
Concerns about creating black holes at the LHC have been thoroughly addressed through comprehensive safety assessments by independent groups of physicists all over the world. The fundamental argument for safety comes from comparing LHC energies with natural cosmic ray collisions that constantly bombard Earth's atmosphere. Cosmic rays from space carry energies up to 10 to the power of 20 electron volts, which is about 10 million times higher than the LHC's maximum energy of 13 tera-electron volts. These ultra-high energy particles create natural collisions with our atmosphere roughly 1 million times per square kilometer every year, and Earth has experienced this kind of bombardment throughout its 4.5 billion year history without any damage at all. If micro-black holes could pose any danger at the energies CERN explores, nature would have already conducted these experiments countless times throughout cosmic history. The fact that Earth and other astronomical objects remain completely intact demonstrates that such phenomena are either impossible or totally harmless. Even if micro-black holes formed but didn't evaporate through Hawking radiation, which would mean Hawking's theory is fundamentally wrong, they would still pose no threat, thanks to their incredibly weak interaction with ordinary matter. They would just pass right through Earth almost without effect, similar to the trillions of neutrinos that pass through our bodies every second, unnoticed.
The future of fundamental physics.
The potential discovery of micro-black holes at CERN represents a lot more than just confirming some exotic theoretical predictions. It would actually mark the beginning of a whole new era in fundamental physics research. Such discoveries would provide the first experimental access to quantum gravity, the long-sought theory that unifies quantum mechanics with Einstein's general relativity. Understanding how gravity behaves at quantum scales could, honestly, revolutionize technology in ways we can barely even imagine, maybe leading to new forms of energy generation, propulsion systems, or even manipulation of space-time itself. The knowledge gained from studying micro-black hole evaporation could also inform our understanding of the universe's earliest moments, as well as its ultimate fate. As CERN prepares for the high-luminosity LHC upgrade and looks ahead to even more powerful future colliders, the search for micro-black holes will continue with unprecedented sensitivity and precision. Every single collision brings us closer to potentially revolutionary discoveries that could reshape our understanding of reality's most fundamental nature. The journey into quantum gravity and extra dimensions is humanity's boldest exploration of the cosmos, probing the deepest mysteries of existence through the power of human ingenuity and international scientific collaboration. Whether or not micro-black holes actually exist, the search itself advances our knowledge of the universe's most profound secrets. CERN's quest to create and study micro-black holes really does represent humanity's boldest attempt to understand the fundamental nature of reality itself. Whether these quantum phenomena exist or not, the search has already pushed forward our knowledge of particle physics, extra dimensions, and those deep connections between quantum mechanics and gravity. As scientists keep pushing the boundaries of what's possible, we're standing on the threshold of discoveries that could transform our understanding of space, time, and matter forever. Thanks for watching Stellar Tech, and don't forget to subscribe for more groundbreaking discoveries from the frontiers of science. A rare visitor from deep space is flying through our solar system. The object, now officially named 3Y Atlas, has astronomers spotting another mysterious interstellar visitor racing through space. NASA's recent data has revealed anomalous features that have sparked intense debate over its true nature. Some scientists fear the possibilities this mysterious visitor presents, suggesting it could be more than a mere comet or asteroid, perhaps even a disguised alien ship. This revelation has generated both excitement and apprehension within the scientific community as we strive to understand its origin and purpose. The breaking discovery. The initial detection of 3Y Atlas occurred in early 2025 by the Atlas Survey System, an automated telescope array designed to spot near-Earth and interstellar objects. Astronomers were immediately intrigued by the object's extraordinary velocity and hyperbolic trajectory that clearly indicated it was not gravitationally bound to our solar system. Dr. Larry Deneau, lead scientist for the Atlas project, confirmed the object's unique path and immediately alerted observatories worldwide to begin tracking this unprecedented visitor. The breaking revelation that 3I Atlas was significantly larger and faster than previous interstellar objects reignited debates about the prevalence of such cosmic travelers. The discovery highlighted the increasing sensitivity of modern astronomical detection tools and emphasized the critical importance of global coordination in tracking these extraordinarily rare cosmic interlopers. Initial observations revealed unusual characteristics that defied conventional explanations for natural interstellar objects. The object's behavior patterns suggested it might possess properties unlike anything previously encountered in our solar system. This discovery marked a pivotal moment in interstellar object research, forcing scientists to reconsider fundamental assumptions about what travels through the void between stars.
The discovery story.
Following the initial detection, astronomers rapidly organized international efforts to gather comprehensive observational data on 3Y Atlas during its brief passage through our solar system. Utilizing powerful instruments including the Hubble Space Telescope and sophisticated ground-based observatories, they systematically confirmed the object's size, composition, and increasingly unusual behavioral characteristics. The European Southern Observatory contributed crucial spectral data revealing complex surface features that appeared inconsistent with known cometary or asteroidal bodies. Dr. Michelle Bannister from the University of Canterbury discussed the significant challenges involved in imaging such a fast-moving, distant object while maintaining the precision required for detailed analysis. The collaborative international effort underscored both the urgency and scientific significance of capturing comprehensive models of 3 and Atlas during its fleeting passage through our cosmic neighborhood. Teams worked around the clock to coordinate observations across multiple time zones and hemispheres. The unprecedented level of cooperation demonstrated the scientific community's recognition that this visitor represented something truly extraordinary. Each new observation added pieces to a puzzle that seemed to defy conventional understanding of interstellar objects and their expected properties. A stranger in our midst. 3. I-Atlas exhibits characteristics unlike any object previously observed in our solar system or beyond. Recent measurements indicate it possesses unusually high reflectivity and metallic surface characteristics that fundamentally defy typical comet or asteroid classifications used by astronomers. Dr. Alan Fitzsimmons from Queen's University Belfast analyzed extensive telescope data, highlighting the strange spectral signatures indicative of advanced materials, rather than natural rocky or icy compositions. Traveling at nearly 60 kilometers per second, the object exhibits unexpected trajectory modifications that some researchers interpret as evidence of artificial propulsion systems. These remarkable anomalies have led a growing number of scientists to propose that 3Y Atlas may represent a technological artifact, possibly an extraterrestrial probe deliberately sent to observe our planetary system. Continued observations aim to definitively determine whether its behaviors represent unknown natural phenomena or constitute evidence of intelligent design and construction. The object's surface appears remarkably smooth and uniform, lacking the typical irregular features expected from natural cosmic debris. Its thermal emissions follow patterns that suggest internal heat sources, rather than simple solar heating. These discoveries have fundamentally challenged existing models of what interstellar objects should look like and how they should behave.
The predecessors.
The previous 2 confirmed interstellar visitors, known as 1I/Oumuamua discovered back in 2017, and 2I/Borisov detected in 2019, provide crucial context for understanding 3I/Atlas. Yet, none of these objects actually share its peculiar characteristics. Oumuamua, for instance, initially baffled scientists with its really unusual cigar-like shape and that completely unexplained non-gravitational acceleration, which honestly just defied conventional physics. In stark contrast, 2I/Borisov displayed classic cometary behavior, showing typical outgassing patterns and developing a visible tail, just as you'd expect from natural objects. 3I/Atlas, though, with its massive size and highly reflective surface properties, fundamentally challenges the notion that interstellar objects always conform to previously known natural archetypes. The growing dataset from these 3 dramatically different visitors is systematically reshaping our understanding of what might actually be actively traversing our galaxy. Each visitor has contributed unique insights while, at the same time, raising increasingly complex questions about the diversity of objects traveling between star systems. The progression from Oumuamua's mysteries to 3I/Atlas's apparent technological signatures really suggests an escalating complexity that, demands serious reconsideration of our assumptions about interstellar space and its contents. The cosmic journey. The cosmic journey undertaken by 3I/Atlas spans potentially billions of years, originating from some unknown star system located far beyond the boundaries of our solar neighborhood. Dr. Davide Farnochia from NASA's Jet Propulsion Laboratory explains that the object's estimated age and remarkable velocity suggest it has successfully survived countless cosmic events, stellar encounters, and gravitational interactions during its extended voyage. Its calculated trajectory indicates a passage through the harsh environment of interstellar space for, potentially over 1 billion years, making it an ancient relic from the early epochs of galactic formation. Sophisticated spacecraft instruments have detected faint emissions, possibly linked to its primordial origin, which offers researchers a unique observational window into materials and processes from beyond our solar system. Understanding this extraordinary journey provides crucial insights into the fundamental processes shaping galactic evolution and the distribution of matter throughout cosmic history. The object's apparent structural integrity after such an immense voyage raises some pretty profound questions about its composition and construction. Natural objects typically show significant degradation after extended exposure to cosmic radiation and micrometeorite bombardment, yet 3I/Atlas appears honestly remarkably well preserved. A scientific goldmine. The discovery of 3I/Atlas represents without a doubt an unprecedented scientific opportunity, with an international array of telescopes and observatories now focused on capturing every possible detail during its passage. Scientific teams from NASA, ESA, and numerous other agencies are collaborating intensively to analyze spectral data, refine orbital models, and systematically search for evidence of non-natural phenomena. Dr. Sarah Seeger from the Massachusetts Institute of Technology emphasizes the extraordinary opportunities this visitor presents for studying interstellar chemistry, exotic materials, and potential technological signatures. The comprehensive data collection effort could, potentially unlock fundamental secrets about planetary formation processes in distant star systems and provide insights into the prevalence of advanced technology beyond our solar system. Each observation is carefully coordinated and scheduled to maximize scientific return during the object's limited time within optimal viewing range. The international cooperation on this project demonstrates unprecedented levels of coordination among research institutions that are typically quite competitive. Advanced imaging techniques are revealing surface details that really challenge our conventional understanding of natural space objects. Spectroscopic analysis has detected unusual emission lines that don't match any known natural materials, fueling speculation about artificial construction and exotic engineering materials. Unanswered questions. Despite extensive international study efforts, fundamental questions about 3I/Atlas remain frustratingly unanswered, leaving scientists divided about its true nature. Dr. Avi Loeb of Harvard University points out that certain observed behaviors definitely defy all known natural processes, including, unexplained acceleration patterns and highly unusual surface reflectivity characteristics. The object's true internal composition, structural configuration, and ultimate origin remain completely elusive despite intensive investigation. Competing hypotheses range from exotic natural cometary remnants to sophisticated artificial probes, potentially sent by extraterrestrial intelligence for reconnaissance purposes. Ongoing research efforts focus intensively on resolving these mounting mysteries, bolstered by significant advances in instrumentation and increasingly sophisticated observational techniques. The international scientific community remains fundamentally divided, carefully balancing healthy skepticism with genuinely open-minded inquiry as new data continues emerging. Some researchers argue for natural explanations involving unknown physics or exotic materials, while others increasingly favor artificial origin theories. The lack of definitive answers has created intense debates within astronomy journals and conferences. Each new observation seems to deepen rather than resolve the central mystery surrounding this enigmatic visitor from interstellar space. The alien question. The possibility that 3I/Atlas represents alien technology has moved from fringe speculation to serious scientific consideration among mainstream researchers studying its anomalous properties. Evidence supporting artificial origin theories includes the object's unusual mathematical heat emission patterns, sophisticated trajectory adjustments, and surface materials that appear inconsistent with natural formation processes. Dr. Seth Shostak from the SETI Institute reports that thermal emissions follow prime number sequences that are extremely unlikely to arise naturally and may represent deliberate signals or encoded information. This finding significantly strengthens the possibility that the object functions as part of a broader network of interstellar probes, communicating through universal mathematical codes that any technological civilization would recognize. The hypothesis suggests systematic interstellar exploration conducted by advanced civilizations using sophisticated reconnaissance technology designed to remain undetected until closely observed. Understanding these potential signals could fundamentally transform our approach to searching for extraterrestrial intelligence and establish first contact protocols. The implications extend far beyond academic interest, potentially representing humanity's first confirmed encounter with technology from another world. Such a discovery would necessitate careful consideration of response protocols and international cooperation in managing potential contact scenarios. Observing the visitor. The global astronomical community has mobilized unprecedented resources to observe 3I/Atlas, coordinating space-based telescopes, ground observatories, and advanced detection systems worldwide. Dr. Nancy Grace Roman's space telescope operations have been specially configured to track the object's trajectory and capture high-resolution images during optimal viewing windows. The Vera Rubin Observatory contributes continuous monitoring capabilities, while radio telescope arrays search for potential technological emissions or communication signals. Dr. Michelle Bannister from the University of Canterbury coordinates international observation schedules to ensure maximum coverage as the object traverses different regions of sky visibility. Advanced spectroscopic analysis reveals surface features that appear artificially smooth and uniform, lacking the typical irregularities expected from natural cosmic debris shaped by millions of years of space weathering. Thermal imaging detects internal heat sources that suggest active systems rather than passive solar heating patterns typical of natural objects. The coordination represents the largest international scientific collaboration in astronomical history, with researchers sharing data in real time across continents. Each observation window provides crucial data that may determine whether humanity faces a natural phenomenon or evidence of extraterrestrial technology visiting our solar system. Dawn of a new era. The implications of 3I/Atlas extend far beyond simple astronomical curiosity, potentially marking the dawn of a new era in humanity's understanding of our cosmic environment. Dr. Michio Kaku from City College of New York suggests that whether this object proves natural or artificial, it fundamentally challenges our assumptions about life, intelligence, and technology in the universe. The systematic study of 3I/Atlas has already driven innovations in observational technology, international cooperation protocols, and theoretical frameworks for understanding interstellar phenomena. These technological and methodological advances position humanity to better detect, analyze, and potentially interact with future cosmic visitors. The growing frequency of interstellar object detections suggests we may be entering an era of regular contact with materials and possibly intelligence from beyond our solar system. Future missions may attempt direct rendezvous with similar objects to conduct detailed analysis impossible from Earth-based observations. The scientific community recognizes that 3I/Atlas represents either an extraordinary natural phenomenon or humanity's first confirmed encounter with extraterrestrial technology. Either conclusion would fundamentally alter our understanding of our place in the cosmos and our readiness to engage with a potentially populated galaxy. The ongoing study of 3I/Atlas continues to challenge everything we thought we knew about interstellar visitors and our place in the cosmic community. Whether this mysterious object represents advanced alien technology or an exotic natural phenomenon, its discovery has already transformed our approach to studying the universe around us. As observations continue and data accumulates, humanity stands at the threshold of potentially world-changing revelations. Stay with Stellar Tech for continued coverage of this developing story that may forever change our understanding of life beyond Earth.